So this talk is about semigroup algorithmic problems in metabelian groups. So there are two things in this title I need to explain. One of them is what kind of semigroup algorithmic problems do we care about? And secondly, what is a metabelian group? So for the first problem, we actually in this talk only consider one problem, which is the identity problem. So it's a decision problem where the input is a set of square matrices S. And the question is whether there exists a sequence of matrices from S such that the product is equal to the identity matrix I. Note that the sequence can have unbounded length, and each matrix can be used any number of times, so it's not obvious whether this problem is even decidable. So in other words, we're given a set of matrices S, and we want to decide whether the semigroup generated by S contains a neutral element, which is the identity matrix. So, of course, the decidability of this problem depends on the size and domain of entry of the matrices. For example, it's undecidable even when the matrices are in SL4Z. So even if the matrices are 4x4 integer matrices with determinant 1. And if we allowed rational entries, then it's even undecidable in dimension 3. And to get decidability, we need to restrict to dimension 2 with integer matrices. So the identity problem is indeed decidable and NP complete when S is a subset of SL2Z, 2x2 integer matrices with determinant 1. So as we can see, while deciding this identity problem is highly non-trivial, and so even in dimension 3, we can get a lot of undecidability results. So maybe instead of restricting the size or entries of the matrices of S, we can better restrict their structure. So this is illustrated by the following theorem. So the identity problem is decidable and in P time when the matrices in S commute. Recall that the identity problem asks whether the semigroup generated by the input set S contains a neutral element I. So how do we understand this theorem? So now let's illustrate how the proof works. Imagine instead of working with matrices that commute with each other and multiplication between them, we simply work in the abelian group Z to the D. Yeah? And let S be a subset of the abelian group Z to the D, which is just a set of vectors. And we want to decide whether this set generates a semigroup that contains the neutral element. So what's the semigroup generated by S? Well, it's simply a linear combination of these vectors in S with positive coefficients. Yeah, and of course, since it's a semigroup, these coefficients cannot be all 0. And we want to know whether the neutral element is in the semigroup. So this is equivalent to deciding whether the following system of linear equations and homogeneous linear equations have non-trivial positive solutions n1, n2 to the nk. So can we find a positive linear combination of these vectors that's equal to the 0 vector? And since this equation is, these equations are homogeneous, instead of solving them over positive integers, we can also solve them over positive rational numbers. They're the same because we can scale the solutions. And therefore, while deciding a system of linear equations, whether this system of linear equations have positive rational number solutions, this is simply linear programming, and this can be done in P time. So therefore, the identity problem in the abelian group Z to the D is decidable in P time. Yeah. But for commuting matrices, now we work with multiplication of matrices instead of addition of vectors. Things can get more complicated, but this remains the key argument. So reducing to linear programming. Okay, so we get this cute theorem, bye-bye. Identity problem is decidable when the matrix is in S commute. To use a more fancy group theory word, we say that the identity problem is decidable in abelian matrix groups. Yeah, it's the same. So now the problem is, can we relax the constraint abelian? Well, because insisting that the matrices in the given set commute is pretty strong. We relax it for a little bit. So this will be indeed the main theorem, the main result of this talk. So we can show that the identity problem is decidable also in metabelian matrix groups. So, well, we relax the abelian a little bit. Of course, I didn't define metabelian yet, but to reformulate it, this means that given a matrix set S that generates a metabelian group instead of a abelian group, it's decidable whether the semigroup generated by S contains the neutral element I. So now, what's a metabelian group? This is the definition. A group is called metabelian if it has a normal subgroup A such that A is abelian and the quotient of G by A is also abelian. So G itself doesn't have to be abelian, but it's constructed using two abelian groups. So it's like a so it's also called a two-step solvable group. So it's a bit more than abelian, but as we'll see, it can already have pretty complicated structures. So what are some examples of metabelian groups? Well, first of all finite groups of size at most 23 is metabelian, but not 24 because S4 is not metabelian. And there are some interesting matrix groups that are metabelian. For example, the Heisenberg group over any field K. So this is the set of matrices, 3x3 matrices that are upper triangular with ones on the diagonal over any field K. And this group is obviously not abelian, but it's still metabelian. And there's a similar example, so the group of 2x2 upper triangular invertible matrices over any field K. Yeah, so yeah, 2x2 upper triangular. Again, this is obviously non-abelian, but it's still metabelian. But the final example, perhaps the most intriguing and the most important, is the Reith product. Again, it's a group of upper triangular 2x2 matrices, but the entries are in the ring of Laurent polynomials. So the upper left entry is a monomial in the ring of Laurent polynomials over D variables. So x1, x2, xd, these are variables of the Laurent polynomial. And on the upper right hand, we have f, which is simply a Laurent polynomial. And if we think about it, by multiplying two such matrices, we still get a monomial on the upper left corner, and again, a Laurent polynomial on the upper right corner. So it is indeed a group. So why is this example important, this Reith product of Z and Z to the D? In fact, it's a classic result that any finitely generated metabelian group can be written as a quotient G by H, where G and H are subgroups of this Reith product Z with Z Reith Z to the D. So here we make a polynomial structure appear. And so instead of solving the identity problem in arbitrary metabelian groups, now we have a concrete group to work on, which is this Reith product. And it suffices to solve the identity problem in quotients of this group. And recall that the identity problem in abelian groups reduces to solving a system of homogeneous linear equations over n. And now, using this group, we'll show the following key proposition. Well, we can show the following key proposition. So the identity problem in metabelian groups reduces to solving a system of homogeneous linear equations over n of x1, x2, xd. So this is the ring, the semi-ring of Laurent polynomials with positive coefficients, meaning all the monomials in the polynomial has to have positive coefficient, plus some possible degree constraints. So there is a similarity with abelian groups, but now the semi-ring over which we solve linear equations is much more complicated. Plus, we have a degree constraint, which could not happen in the abelian group case. So what does this mean? I'll again use an example to illustrate. So what is a system of homogeneous linear equations over Laurent polynomials with possible degree constraints? Here, this degree constraints mean weighted degrees. So for a monomial x1 to the b1, x2 to the b2, the weighted degree of this monomial at direction a1, a2 is simply the dot product of the vector a1, a2 with the power exponent, the degree exponent b1, b2. So an example of such a system is the following. So we have a system of two equations. Here, f1 and fk are variables. So we want to know whether this system of linear equations have non-trivial solutions, f1 and fk, that are Laurent polynomials with only positive coefficients. And we can add possible degree constraints. For example, we can add the following degree constraint. We need that at the weight 3, 2, the degree of f1 is larger than the degree of fk, and at weight a2, where a is between 0 and 3, the degree of a1 is strictly larger than the degree of fk. So we can have a combination of such a weird degree constraints. And we want to solve such systems. So our key proposition says, to solve the identity problem in metabelian groups, it suffices to solve such a system of homogeneous linear equations over this polynomial semi-ring. So how do we solve such systems, assuming this key proposition? How do we decide whether a solution exists? It's highly non-trivial, but we can look at some examples. So for example, does the following equation have solutions over n of x, positive coefficient polynomials? Now it's not super obvious, but actually the answer is no. There's a trick to proving this. We evaluate this equation at x equals 3. And this equation becomes, well, p1 of 3, well, p1, p2, p3 are polynomials. So p1 of 3 plus p2 of 3 plus 2 times p3 of 3 is equal to 0. But this cannot happen because p1, p2, p3 are polynomials with positive coefficients. And when evaluated at 3, they're both positive, and 3 positive numbers cannot add up to 0. So this equation does not have any solution over n of x just by this evaluating trick. So let's look at another example. Well, does the following equation have solutions over n of x satisfying this degree constraint? So P1 has to have larger degree than P2, which has larger degree than P3. Now we can't use the same trick because it's easy to see that with whatever positive real number we plug in, there will be no contradiction. So we need to utilize this degree constraint. So again, the answer is no, because if there were such a solution, then the degree of the first term would be too big. It would be bigger than the degree of the two other terms. So they cannot add up to 0. Yeah, so there are these contradictions. And in fact, we can show that these two types of contradictions are the only type of contradictions possible. That a system of homogeneous linear equations with possible degree constraints has solutions if and only if no contradictions of any of the two types can happen. So, well, the proof is, again, quite technical, but it combines real algebraic geometry with positive Stellensatz type arguments and tropical geometry, which consists of gluing up Newton polytopes. And once we can prove this, we then can use a double procedure to decide the existence of solutions. So now instead of trying to find solutions, we can have two parallel procedures, one trying to find solutions and the other one trying to find contradictions. And one of them must stop thanks to this local global principle. Yeah, so now we get decidability. To summarize the procedure, we reduce the identity problem in metabelian groups to the identity problem in the quotient of the Reith product. And then by our key technical proposition, we reduce it to solving system of homogeneous linear equations over positive polynomials with positive, with degree constraints. And then we solve such systems using real algebraic geometry and tropical geometry. Therefore, we get decidability of the original identity problem in metabelian groups. Okay, that's it for my talk. Thank you.